So hello everyone, this is ADITYA MISHRA and welcome to this second lecture in lecture series on aerodynamics. Like I have previously told, these lectures are meant for students willing to take up aeronautical or aerospace engineering in their higher education. Also for those students who are willing to appear for and crack the GATE examinations. For job seekers, like I have already told, the term aerodynamics itself is has wide range of application in practical life, and it is applicable on train, bus, building, and any object which is moving through the air. So in previous classes we have discussed some of the fundamental things which is needed. In this class also we are going to see some of the fundamental concepts which are useful for investigating or studying aerodynamics, particularly everything which is you can say can be written on paper, how to representing aerodynamics in mathematical form and on paper. uh, some of the ideas which is important, that is what we are going to study. So to begin with, actually we'll talk about Bernoulli's principle, which helps us in understanding how lift is actually generated over the surface of an aerofoil, and how the aerofoil is actually lifted when it moves through the air. Okay, so the Daniel Bernoulli actually came up with this expression for an incompressible one-dimensional flow along the streamline. He came up with this formula, which is summation of pressure energy and kinetic energy. The formula says that the pressure energy and kinetic energy for an incompressible and ideal flow remains constant everywhere along the streamline. Right. To understand this use of this expression, let us first see what happens over the aerofoil surface. So this is an aerofoil, as all of you can see, and the upper surface of the aerofoil is actually a little curved compared to the lower surface of the aerofoil. In real life applications, the lower surface is nearly flat or almost flat. So if we talk about continuity principle, or through the continuity, if the fluid particles which are approaching the aerofoil, these fluid particles actually gets separated in two different streams. Okay, the upper particles, they have to travel a larger distance because of the upper curved surface, and the particles on the lower surface, they have a lesser distance to travel, right? And to reach, let's say for example, if the particle started from this particular position, from the leading edge of the aerofoil, and the particles have to reach in same time to the trailing edge, then definitely the particles which are on the upper surface, they have to travel larger distance compared to the particles on the lower surface. So to reach in same time from the leading edge to the trailing edge, the upper particles have to run faster compared to the particles on the lower surface, right? And to understand how this is related to this equation, you can actually see that there are only two terms. One is velocity term and another is pressure term. Okay, when we say the particle is moving faster, the velocity is high on the upper surface, and the velocity of the fluid is low because it has to travel a lesser distance. The velocity is low. So because the velocity on the upper surface is higher, the pressure has to be lower in order to keep this entire term constant, right? And because the velocity on the lower surface of the aerofoil is lower, the pressure term has to be higher. So definitely, like we have discussed, the pressure, because the velocity on the lower surface of the aerofoil is less, because of less distance need to travel by the particles, the upper surface has more distance, the sum total has to be equal to 0. So wherever, when the pressure increases on the upper surface, when the velocity increases, the pressure decreases, and on the lower surface, as velocity decreases, the pressure increases. So if we apply this equation between 2 points at the front portion and rear portion of the aerofoil, the equation takes this following form. And as you can see, the pressure here, like we have discussed, P2 is definitely more than or greater than the pressure on the upper surface. The equation takes this following form. So therefore the particles or motion of the particle, the fluid, has to maintain constancy in the sum of these two values as it moves from point 1 to point 2. The pressure on the upper surface is more, sorry, lower surface is more, and the pressure on the upper surface is less. So that's what how Bernoulli's principle is helpful. Then because of the movement of aerofoil through the air, the aerodynamic forces which are set up over an aerofoil is here visible. If the aerofoil is inclined, let's say the flow is moving from this particular direction, the resultant aerodynamic force will try to throw this aerofoil in the direction of the force which are acting from the bottom surface. So dividing this entire force, resultant aerodynamic force, we get two values. One is lift and another is drag. Lift force is responsible for raising the aerofoil higher in the air as it moves in forward direction, and drag forces are responsible for slowing the aerofoil down when it moves through the air. Again, a simple representation would be this. As you can see, the relative wind actually coming from the forward direction pushes the aerofoil in backward direction, but because the surface is inclined here, if we keep the surface inclined here, the like a kite, it is going to raise high or fly in the air. Right, so two most important forces when we are talking about a flying vehicle or flight vehicle is lift and drag. Right, now how this lift and drag, like we talked about Bernoulli's principle, the pressure on the upper surface of aerofoil as it moves through the air is lesser, uh, or a suction, you can say, compared to atmospheric pressure or atmospheric pressure. A suction region is created, low velocity, low pressure region is created on the upper surface. Comparatively, a higher pressure acts on the lower surface, so a high pressure is set up at the lower surface, which the difference on pressure, like if this is an aerofoil, the upper pressure will have a less value, and the difference of pressure, the resultant value, is going to push the aerofoil in the upward direction from the downward direction. Right, the resultant force will be acting in, lift force will be acting on the aerofoil, which will make the aerofoil soar higher. So the lift in any flying object is generated because of the pressure difference. Right, this is one of the most important thing which we should remember when we are trying to study aerodynamics. The lift is created by difference of pressure. Then coming to concept, a most important concept which is important for theoretical aerodynamics. It is very widely used concept. Actually it is practically, actually it is nearly looks like it is difficult to understand circulation. However, mathematically it's a very important concept which is helpful in explaining many of the physical phenomena observed in real life when an aeroplane is moving through the air. So what is concept of circulation? When a fluid flows over the surface of the aerofoil in this region, we can actually talk about it. The velocity over the surface of aerofoil is represented somewhat like this. So you can see these velocity vectors, they have a different length. Okay, a smaller value is here, a larger value is over here. So when these velocities are subtracted, when the velocities on the upper surface and free stream velocity, actually when the free stream velocity are subtracted from all these velocity vector points, then a different scenario comes up in the picture. The resultant velocity, when we take the difference of free stream velocity and local velocity which is on the surface of aerofoil, it results mathematically. Visualizing this picture appears somewhat like this, which is there in picture number 2. Okay, so from this application or from this observation, mathematicians actually came up with the idea of circulating flow. So there is another, so definitely when a fluid moves through the air, theoretically we can come up with an idea of circulation, that there is some phenomena which sets the fluid circulate around the aerofoil. Okay, so that is this phenomenon, and this mathematical representation is actually treated as called as circulation. Okay, so like I told previously also, circulation, it is basically a hypothetical concept, or we can also call it as a mathematical tool to understand or to represent the aerodynamic studies or on paper. Also, this concept is very widely used in to explain concepts in theoretical aerodynamics. In developing concept of aerodynamics on paper, it has been, the idea of circulation is very widely used. Also, it forms one of the basis or the building block of theoretical calculations when we say a term called circulation. Then coming to next very important thing, like I said, mathematically it is also defined as line integral of tangential component of velocity over a closed surface. So let's say we have an aerofoil which is placed in air, and over this aerofoil which is moving through the air, we want to calculate what is the value of circulation. So we can draw any arbitrary closed contour around this aerofoil, and to calculate this the value of circulation on it, we first need to have some, let's say we take a piece of this closed surface or closed loop, which is having area ds, and let's say the velocity of which is crossing this surface is v, and like the definition said, the circulation value is tangential component of velocity. To bend this velocity vector through an angle alpha, we end up getting a cos alpha. So mathematically we say it is represented, circulation is represented by a line integral, a single integral of velocity component and velocity vector and area vector, which can also be simplified and represented in this form. So circulation is nothing but mathematically it is a line integral of tangential component of velocity over a given surface, and if we integrate over this entire surface, we'll end up getting what is the value of circulation for given flow velocity, given pressure, and the amount of lift. We will also see it can be easily calculated using the value of circulation. So then again, after circulation, one of the most fundamental idea for circulation or the theorem for circulation is Kutta-Joukowski theorem. Kutta and Joukowski, these two scientists, came up with the statement or this value for two-dimensional incompressible flow and ideal flow. It simply says that lift per unit span over a two-dimensional cylinder. Two-dimensional basically means any object which has no end. It is extending from infinity to infinity, and in previous class we have seen that how this thing can be achieved or attained in real life when we are actually working inside the laboratory conditions. So it simply says that lift per unit span is proportional to the amount of circulation, right? So lift can be calculated from the value of circulation, and which is very important for aerodynamic performance of the aerofoil shape. So basically, in order to understand, let us take up an two-dimensional cylinder. As I said, it is extending from infinity to infinity, which means it is endless. The cylinder is endless. So over this endless cylinder we can have, let's say b for the time being is the value of a span. Actually infinity also doesn't mean that it is endless. the another way of looking at infinity is that we are paying attention to a very small piece of an object or very small part of an object. So to compare to that part, the length of the object is very large. So that is another way of looking at an infinity. When we say the focus is on very small portion of this object, so it looks, the entire object will appear to us as infinite in length, or it takes a larger distance to reach to this. So if gamma is the overall circulation over this entire cylinder, okay, this again, this whole thing can be viewed in a different way. So let's say if this is a cylinder, the entire picture can be, okay, so if this is a cylinder, if the entire picture can be considered in a different manner, like the circulation is distributed over this entire surface. Okay, so when we calculate the end over this entire span length, the total circulation would be represented by like this lift per unit span, which means the total lift which is generated when we divide it by the total span or span length or total length of the object, it will be called as lift per unit span. And according to Kutta-Joukowski theorem, it is directly proportional to the total or resultant value of circulation, which could be uniformly distributed somewhat like this over the entire surface of the object, right? And to remove this proportionality, we came up with an equation, and then this constant term is represented like this. So according to the Kutta-Joukowski theorem, lift per unit span, which actually implies that in every centimeter or every unit length of a cylinder, the value of lift could be calculated from the value of circulation or total circulation. The circulation value is constant over the entire length. The combined effect could be can be represented using single values like this we have represented here. So it is one of the most important formula which is applicable for more some of the most basic calculations, fundamental calculations when we are talking about flight vehicles or aeronautical or flying objects. Fine. Then next important thing is Kutta condition. So this is one of the most interesting uh, condition actually put up on the surface of aerofoil, which helps in deciding increasing the lift of an lift generated by an aerofoil. So as we can see here, whenever an air moves or if an aerofoil is kept inclined to the surface, over the aerofoil surface, actually there are 2 points where the stagnation is flow gets stopped or it reaches to zero velocity. One point is near the leading edge on the lower surface, and another point is on the near the trailing edge of the aerofoil on the upper surface. Now this separation actually could result in loss of lift. So a condition, Kutta condition, basically helps us ensure that the flow on the upper surface of the aerofoil or actually over the entire surface leaves very smoothly. Okay, so to better understanding, let's take this idea. So like I told you, there are two stagnation points, 2 points where the flow stops or which the flow is at zero velocity. One is point P and another is point Q. Now by increasing the value of circulation, we'll see in the coming part, by increasing the value of circulation, this value could be detached or removed from the surface, from the upper surface of the aerofoil, or the stagnation point which is formed near the trailing edge of the aerofoil could be actually delayed or maybe removed from the surface of the aerofoil. So Kutta condition therefore serves a purpose of removing this separation point and increasing the lifting capabilities of an aerofoil, conventional aerofoil surface actually. So given a sufficient value of circulation, actually the separation is delayed, okay, and the surface of aerofoil could produce, or basically an aerofoil could generate more amount of a lift if this point is delayed. So Kutta condition serves the purpose of maintaining a smooth flow over the aerofoil, or you can say it is a condition which is established to ensure smooth flow, or flow which is leaving the trailing edge to move smoothly, okay. Then it also results in increase in lift. What does the Kutta condition say? Like I said, it helps us to establish a smooth flow over the surface of the aerofoil, because which is near the trailing edge. What does it say? It implies that it says that for a given aerofoil, for any given, for a fixed angle of attack, at one angle of attack, for given shape of the aerofoil, there is only one value of circulation for which the flow leaves the trailing edge smoothly, right? And there are conditions for the finite, if the trailing edge is actually pointed and straight, and second one if it is curved or bent in the shape of S. So we'll talk about this in coming classes. And most importantly, if we want to see, visualize how the increase in value of circulation actually helps to you can say delay or move backward this second separation point. In the first picture, as we can see, it is at here on near the almost one fourth of distance from the trailing edge, and as the value of circulation is increased, it is actually getting moving in the backward direction. So with a given value of circulation, it is possible to have a flow over the aerofoil leaving trailing edge smoothly. So this is one of the most important condition which is very difficult to attain in real life conditions, at particularly at very high speed conditions. Then another interesting thing in aerodynamics or aeronautical part, when we talk about flow over an aerofoil, is formation of an starting vortex. Starting vortex is basically a vortex which is formed when the flow actually starts or commences over the aerofoil. So for the first time when the flow moves over the surface of aerofoil, actually the flow from the lower surface moves in upward direction and causes the flow to separate ahead of the leading edge from the upper surface, right? With further increase in velocity, or when the flow moves downstream at the trailing edge, high velocities results in curling of a flow, and this curling of a flow actually results in the formation of a vortex. Actually, so this vortex actually sets the entire picture for theoretical aerodynamists to study the concept of lift generation over the surface of aerofoil. And because the upcoming flow which is coming free stream, which is actually following the air which is blowing over the surface of, or moving from on the surface of aerofoil, causes this vortex to get detached, okay. So the starting vortex is actually formed in the beginning for the first time when the air moves over the surface of aerofoil, and the detachment of this these vortex actually results in generation of steady lift on the surface of aerofoil. So basically the entire picture looks like this. Initially this vortex is on the surface of aerofoil. The upcoming air pushes this vortex to move in the downward direction till a steady circulation value is attained on the surface of aerofoil, and the aerofoil or the wing is ready to lift up, right? And then one of the most interesting concept or theorem related to this is Kelvin's circulation theorem. The circulation theorem simply says that the change in circulation over time for a given closed surface which is formed by same particles anywhere in the entire flow field will have a constant value of circulations. To understand it better, let's say, so circulation around closed curve which is formed by set of fluid elements in a flow remain constant. So for example, let's say these are the fluid particles which are moving in a flow, and at a given time, for at a given instant of time, if we trace all these particles and join them by means of a curve, they will have, for a closed surface we can calculate the value of circulation, right? As these fluid particles, they move through the flow field, they change their position, right? But again, if we trace them by means of a closed curve, according to Kelvin's observation, which is based on experimental setup, the circulation over these particles maintains the same value. Okay, so the curved formed by closed curve, which is formed by tracing same fluid particles anywhere in the flow field, will have the same value of circulation. So in short, this can be written as rate of change of circulation is 0, and therefore the circulation remains constant over the closed surface which is formed by same particles anywhere, anytime in the flow field. So that's all for today. Thank you very much, all of you. I hope this is useful, and we'll meet with new concept in the next class.